Have you ever tried listening to a faint radio station, only to hear static and other sounds drowning out the music? Or perhaps you have attempted to understand a conversation in a very loud, crowded room. In both scenarios, an underlying message is being obscured by unwanted interference. In the fascinating world of neuroscience, noise in the context of neural signals refers to any random, unwanted electrical or chemical fluctuations that interfere with, or obscure, the genuine neural activity we are trying to measure or analyze. It is not necessarily a malicious force, but rather extraneous information that makes it harder to discern the true signals of the brain. The primary reason noise is so prevalent stems from the incredibly complex and dynamic environment of the brain and the surrounding body. Noise can originate from various sources. These include biological artifacts such as muscle activity during movement, eye blinks, or even the electrical activity of the heart. Additionally, environmental factors like electromagnetic interference from power lines or other electronic devices, and instrumental limitations such as imperfections in recording electrodes or the cables themselves, all contribute to this pervasive interference. Each of these sources generates tiny electrical potentials that get inadvertently mixed with the specific neural signals we are attempting to observe. Dealing with noise is a fundamental aspect of neural signal processing, and researchers employ several techniques to mitigate its effects. These include various filtering methods, such as bandpass filters to isolate specific frequency ranges of interest, or notch filters to remove known interference like 60 Hz power line noise. Signal averaging can also be used, where multiple repetitions of a signal are averaged together to reduce random noise while preserving the consistent neural response. Proper experimental design, including shielding and grounding of equipment, is also crucial. Understanding and quantifying noise is so critical that neuroscientists frequently discuss the signal-to-noise ratio, often abbreviated as SNR. This metric compares the power of the desired signal to the power of the background noise. A higher SNR indicates a clearer signal and more reliable data. It is important to remember that some noise is intrinsic to biological systems and even the physics of electrical measurement, much like thermal noise in electronic circuits. The goal is not always total elimination, but rather to maximize this SNR. By comprehending the nature and sources of noise, and by employing robust mitigation strategies, neuroscientists can more effectively extract meaningful information from neural activity. This deep understanding allows them to make more reliable discoveries about brain function and to develop more accurate and effective neurotechnologies, ultimately helping us to better decipher the intricate language of the brain.